Hi everybody, my name is Natalie Mihajcik and I'm a PhD student at Worcester Polytechnic Institute in NestLab. Thank you for attending my remote ICRA 2020 presentation. In this video, I will talk about our work designing SwarmMesh, a distributed data structure for cooperative multi-robot applications. Our end goal is to work towards enabling autonomous multi-robot applications in scenarios where robots have to collect a lot of data without an existing communication infrastructure, besides their ability to exchange messages. We proposed a shared data structure that facilitates the collection and management of data in a distributed fashion. The data we consider can be of different types, such as an expanding firefront, a safe path, or victims to rescue. Together, this data forms a shared world representation that changes in time and space. At its most fundamental level, our data structure stores the data as tuples. Every tuple is identified by a key that corresponds to a data type and a position. In addition, every tuple has a custom payload that encodes type-specific data. So for instance, a fire could be encoded in a tuple with the key fire, and the value could be the radius of this fire. A victim could be included by a tuple with the key victim, and the value being the priority to rescue this victim. In our work, we consider three types of realistic constraints. The first one is that robots allocate a limited memory to the shared data structure. We assume that the amount of data to store is much larger than this quota. In this way, the rest of the memory is available for the robots to perform complex perception and decision making. The second constraint we consider is limited communication bandwidth. We want the robots to devote as little bandwidth as possible to the housekeeping required by our data structure. The third constraint we consider is that the communication topology is highly dynamic due to the fact that robots are free to move according to mission requirements. The fundamental question in our paper is which robot should store what data and when. One important aspect of designing a distributed data structure is the amount of data duplication. One extreme is allowing full duplication of the data at each node, and the other extreme is keeping a unique copy of a tuple across the entire data structure. This previous work in swarm robotics addressed the constraints of low bandwidth and high mobility nodes, but allowed eventual full data duplication. In our case, we want to use as much as possible the collective memory, with only a controlled amount of duplication for robustness. Another consideration that ensues from not being able to duplicate data fully is organizing the distribution of data to nodes and organizing the data flow between the nodes. Deciding which node stores what data is referred to as key partitioning in peer-to-peer network literature. The data flow between nodes happens based on an overlay network. Some distributed hash tables use a structured topology for the overlay network, which makes data routing very efficient, but is not practical with high node mobility. Work by Ratnasamy and sensor networks considered nodes moving in space. The main difference with our approach is that the end goal is to offload this data to a server rather than keep it over time for all nodes to use and update. The main insight in our work is that certain robots are more desirable to store data than others. To decide which robots should store the data, we want to use information that is available to the robots locally and instantaneously. In our work, we consider the number of neighbors of the robot and an amount of free memory. This robot is a good candidate to store new data because it is well connected and has a low memory usage. This means that it would be easy for this robot to reply to data requests and hold on to the data for a long time. In contrast, these robots at the periphery are not well connected and are likely to have to transfer part of their data elsewhere. Therefore, we decided to characterize this property by a robot node ID, which is higher with a higher number of neighbors and more free memory. The other side of the question of which robot should store which data involves considering how data differs. We consider that the type of data collected can be prioritized. For instance, we consider that data about victims is of the utmost importance, then data about fire follows, and so on. With those insights, we decided that data of more important types should be stored in robots with higher node IDs, because those robots are better connected and can send the data out to many other robots. In the paper, we tested 2 ways of partitioning the keys to match data to robots. One of them is based directly on the type of data. We directly map more important data types to higher data hash values. The node ID of the robot is the product of its number of neighbors and its amount of free memory. And a robot can store a tuple if its node ID is higher than the data hash. This shows the realization of our shared data structure in a simulated environment. The colored spheres represent events of different types. If we zoom in on a particular robot, we can see its node ID, which depends on how many neighbors and how much free memory it has. This robot is already storing some tuples. When the robot records an event of type orange, it considers the value of the hash assigned to that color and stores the tuple if its node ID is higher than this hash. This whole process is happening across the whole robot team, with robots recording events and sending tuples they cannot record to better suited robots. We are showing a case where robots are making a heavy usage of the data structure. Robots can make queries on the data structure. For instance, this robot has requested all tuples of type black. The query is flooded throughout the network, but the replies are then routed back following a hop gradient. We provided several operations in our implementation. They are detailed in the paper. We stress tested the data structure to verify that we were able to retain large amounts of data appearing very quickly. We pushed the load of to the amount of data a centralized data structure could store. And we recorded near zero occurrences of robots having to discard data due to storage memory overflows. When the key partitioning is poorly designed, we noticed an increase in communication overhead. This illustrates a good partitioning of the data keys because the histogram of robot node IDs is to the right of the histogram of data keys. This means we have enough robots with higher node IDs than the data. Those robots can store the data. A poor partitioning would be this situation where robots cannot store most tuples. In this graph, we show the percentage of tuples in storage memory. We allow the robots to keep a routing queue for tuples they cannot properly store. The top lines show that with good partitioning, we reach a steady situation in which tuples are kept in storage memory. The bottom lines show that in case of bad partitioning, most tuples are not kept in the permanent storage memory, but rather they're shuffled around, which increases the communication overhead. The way to optimize this key partitioning is an open question of this paper and will be the subject of future work. In conclusion, we designed a distributed data structure for low memory, low bandwidth, and highly mobile multi-robot systems. We tested it in realistic simulations with different metrics across different parameters and obtained good results. Thank you for your attention.